Microscale linear accelerometers are small microelectromechanical systems that can detect acceleration in one direction. In this application, a linear accelerometer is designed for system monitoring in a twin-screw extruder. The extruder is part of a cryogenic research project being conducted to characterize the production of solid pellets made of so-called heavy isotopes of hydrogen. These are deuterium and tritium. These pellets will be used to fuel fusion energy plasmas in experimental projects like ITER and JET. Because the mixture is nearly solid as it is forced through the nozzle, there is a great deal of stress on the driving screws. Any additional restrictions could cause catastrophic failure of the device, such as solid inclusions in the mixture or improper screw speed. These problems could be detected by implementing a linear accelerometer mechanically fixed to the extruder case. With it, the operator can find the optimal speed with the least amount of impedance, or a safety shutdown circuit could be designed to stop the screws in the event of a strong vibration. This application is vital in prolonging the life of the extruder, reducing noise in the data acquisition system, and ensuring safe operation. The design of the sensor has very specific design parameters. Current cryogenic vibration sensors, like the Dytran 3045A, are made for general purpose with a minimum temperature of 20 Kelvin and a bulky capsule. This application calls for a sensor no larger than 25 by 25 by 25 millimeters cubed to fit in the device closest to the source of vibration. Being that close to the hydrogenic mixture, the sensor must be accurate in conditions down to 10 Kelvin. With MEMS fabrication limitations on finger spacing and relatively low vibration forces, the accelerometer must have a displacement sensitivity of 10 nanometers per gravity acceleration. Lastly, the vibration detector must output a signal that can be detected and analyzed by a data acquisition system. The solution to the design constraints is a capacitive linear comb accelerometer with folded beam support fabricated by common MEMS techniques. There are generally two choices for making an accelerometer sensor: capacitive or piezoelectric. Capacitance is more linearly related to temperature variations than piezoelectric effects and is therefore a better choice for this application. As shown in Figure 4, sensitivity is linearly related to the proof mass size, so making it as large as possible will enable the sensor to detect even weak vibrations. Making robust interdigitized fingers will help reduce the effect on capacitance from thermal expansion and contraction. Packaging both the comb accelerometer and an energized circuit will produce a detectable voltage for manipulation by system monitoring circuits. Finally, placing the sensor in a hermetically sealed, slim stainless steel capsule with a single threaded stud will fit the size constraint and will thermally isolate the sensor from adding heat to the system that would alter its characteristics or freeze the accelerometer. A stainless steel case makes a good thermal barrier because stainless steel's thermal conductivity is less than 10 watts per meter Kelvin at cryogenic temperatures, and sealing the device in a vacuum adds to the thermal barrier. This design for a vibration detector meets all the design constraints for the very unique cryogenic application.